Okay, so I'm going to talk today mostly about the tectonic applications that we use MT for. As Jim said, it's used widely in mineral exploration, geothermal, and in hydrogeology. But I'm going to talk about how we use MT to understand plate tectonic processes with a number of applications. So, as is familiar, we have the map of the Earth with the various tectonic plates. All the motion pretty much occurs on the plate boundaries, where we have convergent, divergent, and transform boundaries. We have a lot of processes going on that can be studied with geophysical methods, seismology, GPS, INSAR, and MT. And a particular emphasis I'm going to focus on today is the fluids. So a lot of plate tectonic processes we know are very sensitive to the presence of fluids. Fluids can often control the rheology of the crust and mantle. Very small amounts of water in particular will change the strength of a rock. And the rock is very much, the resistivity of the rock is the parameter that we're using in MT, and that's often very sensitive to fluid content. So MT started out, back in the 1950s, a very primitive method. And as you all know here from EarthScope, with the US array having this MT component, it's really, I think, raised the profile, and it's also improved the method. So kind of a theme I'm going to try and emphasize is how we can make measurements of fluid distribution in the Earth from electromagnetic measurements. So I'm going to use the acronym MT, which is short for Magnetotellurics, and I'll introduce the method, and as we go along, just try and give you a sense of what we're actually measuring and also what the resolution is, which is often a key thing. So first thing I'm going to start out talking about resistivity of rocks. And I tend to use a color scale. There are certain geology departments I've visited sometimes where it's best to stick with numbers, and color scale works pretty well. Other places, the numbers are fine. But basically, rocks' resistivity varies over at least 3 to 4 orders of magnitude, in contrast to seismology, where we're looking at, factors of 2 or 3. So high resistivity rocks, such as igneous materials, they are basically dry. There is nothing that makes electricity pass through them. On the other hand, a lot of rocks in the Earth can have a very low resistivity, and that's because of the presence of salt water, perhaps because of partial melts, or some other conducting phase. In between, sedimentary rocks have a typically intermediate resistivity, and that's because we've got pore fluids, which are often saline, which conducts electricity. So I generally will use cold colors for the resistive material. It's dry, it's cold. Any rocks that have a low resistivity will have a red or a yellow color. And trying to understand how we go from a resistivity measurement to rock properties does depend critically on lab measurements, such as Jim and colleagues have done over the years. So interpreting resistivity data is complicated. And Anne Pommier, who's now moved on from here, she's made available some very useful compilations that we've all benefited from. So the basic problem is, if we see a low resistivity, there's lots of explanations. It's non-unique. It could be molten rock, it could be salt water, it could also be graphite. If we're doing mineral exploration, it could be massive sulfides. All of those things produce a low resistivity. And we need extra information to figure out what it could be. On the other hand, if you see a very high resistivity, it's relatively non-unique. If we see 1,000 ohm meters, that rock is dry, it's probably cold, and it doesn't have sulfides or graphite. So high resistivity is unambiguous, whereas low resistivity has multiple explanations. Well, not going to be many equations today. This is perhaps one of two. Lots of rocks, we have to consider that they are two-phase materials. And a simple example would be here, where we've got a sedimentary rock, highly resistive grains, could be quartzite, and in between we have a pore fluid, which could be salt water, could be oil, could be gas. If it's salt water, this is going to be the material that conducts the electricity. And we can choose an empirical law. There's others around which are perhaps more well justified, but Archies Law has been around for 50, 60 years, still widely used, and it relates the porosity of a rock, shown here, to the bulk resistivity. So what we're doing is we're averaging highly resistive grains with very low resistivity fluid. And what we can see is, as you increase the amount of fluid, the resistivity comes down. So this is the porosity. And Archie discovered an empirical relationship which allows you to link porosity, fluid quantity, with resistivity. permeability also comes into it. Obviously, these pores could be isolated and not really have a big effect on resistivity. So permeability comes into Archies' law through this exponent. And again, it's lab experiments which are really key here in interpreting the data. So I think the last 10 years has been a real improvement, certainly with igneous rocks, with melts, where this is how this works. So Archies' law was developed for sedimentary rocks, for oil and gas exploration, but it's now can be widely used where the fluid is partial melt. You can have a system of resistive grains, and you've got silicate melts on the boundaries acting as the fluid, because in the silicate melt, it conducts electricity very well. Ions can move through. Okay. Well, here's an example of how one of the extra things we need to know about partial melts. As a rock melts, minerals have different melting points. So as a rock begins to melt, we start to accumulate melt according to the melt percentage here. And one of the things we can see is that several distributions of melt are possible. In one case, we have the melt accumulating on the grain boundaries. In the other case, because of the dihedral angle, the wetting angle, the melt actually will be isolated. And obviously, this is going to have a huge difference in terms of the resistivity. In this case, there's a nice pathway for electric current to flow through. In this case, the electric current has to still flow through the resistive grains. So again, lab experiments have been really quite important in this area. And studies of partial melts are needed to actually understand which of these configurations is present in a system. So for a lot of basaltic melts, you actually see, here's a lab experiment by Martyn Unsworth's group in the Netherlands, and they showed here from a quenched basalt, you can see the dihedral angle is pretty low. The melt will connect quite easily. But every system that you work with, you move to more felsic rocks, you have to kind of answer this question. And sometimes, depending on the water or the carbon dioxide concentrations, that can change everything. So the connectivity of the melt is critical here, and lab experiments are needed to really understand and interpret resistivity data. So I'm going to mostly be talking today about systems of partial melts, but also some where we have water dissolved, which is needed to understand the resistivity of a rock. Well, a little bit now about how we make these measurements. It's one thing to measure the resistivity of a rock when it's sitting on the bench in the laboratory. When that rock is underground, it's a little bit more complicated. And MT is a passive geophysical method. That means we're using electromagnetic waves coming from the atmosphere. And according to the frequency, they will penetrate into the Earth a different distance. So the blue is an incident wave, and the red is reflected. So most of the energy is reflected. Actually, there's a lot of artistic license in this figure. It's about 0.1% transmitted. So what you can see is the signal, the low frequency signal here, which I took as 10 hertz, is making it down a few kilometers. The higher frequency is only going a kilometer. So what we do is in MT is we measure the electromagnetic fields at the surface, and from the ratio we can calculate how deep the signal is going and what is the resistivity in the region that it's sampling. So in contrast to seismology, seismology has sources within the Earth that are coming upwards. In MT, they're coming from the atmosphere and going downwards. So that obviously introduces some limitations on how deep the signals will go. Where do they come from? Basically above 1 hertz, all of these signals are coming from global lightning activity. Here is a lightning strike on our campus on the Faculty of Engineering, but didn't do too much damage apparently. And below 1 hertz, these signals are coming from the magnetosphere, from the aurora. So the solar wind is changing and produces these low frequency changes in the geomagnetic field. So 1 hertz is about the boundary. But obviously, as in any passive geophysical method, the signals are not always guaranteed to be there. So high frequency lightning strikes are pretty predictable. Low frequency, these are coming pretty much from the magnetosphere, controlled by the 11-year sunspot cycle. So every 11 years, the people who do MT have this sort of period of kind of angst and worry, and the signals get really weak. And the last minimum was really weak, and a lot of people said maybe the sunspots have gone away forever, or for another few cycles. So as we approach the lower frequency minimum, the EM people will start to get nervous. Seismology doesn't have any such problem, I don't think. Several of my colleagues even said, oh, well, we'll become seismologists if the MT signals don't come back. And in a few cases, we all thought, oh, good. But anyway, that didn't happen. So that's a little bit about the MT method. So in the field, I apologize, this talk had an incarnation of being in Spanish for quite a while, and this one slide didn't get translated back. But this is showing how we actually make these measurements in the field. And this is looking down at a map. So we measure the electric field in two directions. We bury electrodes, and we have a cable that's up to, say, 100 meters long. So this is basically a voltmeter. We're measuring millivolts of electric field in two directions. And the magnetic fields are measured with these larger coils, induction coils shown here. And these need to be immobilized like a seismometer. And this is what we spend most of our time in the field, is digging holes for these things. This is in Yucatan at Chicxulub about 15 years ago, where there is not much soil, and a lot of our time was spent with locals with pickaxes trying to break the rock. Because if the coil moves, it's moving in the Earth's fixed magnetic field, it's noise. So these things have to be immobilized. You could make these MT measurements in the air. In principle, the field's the same. But it's just practically much easier to put the sensors just below the surface of the Earth. So you can make the magnetic field measurements without touching the ground. And there are geophysical methods that use airborne helicopters to do that. But for the electric fields, you have to connect with the Earth and make those measurements. So somebody could find a good way of doing MT without laying 200 meters of cable out. It would make a huge advance, but it's very difficult to make that measurement. So here you can see this is an older version of an instrument that we were using back at about 2000 from EMI in the Bay Area, and data recorder, battery, and a disk drive. Sit in the field. Typically for a day is the measurement we're making to get these frequencies. If you want to measure really low frequencies, you have to sit there for a long time. So everything goes with frequency. High frequency is near the surface. Low frequency is deep, so you can go from 100 meter penetration to 100 kilometers, the same equipment. So you can separate the structure with depth. Well, this one picture here shows kind of one of the banes. We make the horizontal magnetic field measurements. They're easy, but shown here is one vertical sensor. And putting this one in often takes longer than the whole rest of the instrument. You know, digging a 2 or 3 foot vertical hole is kind of sometimes a little bit of a chore, let's put it that way. And some students think we can use the drill a lot, but quite often it's just the 30-pound metal bar is what you have to use. So I'm going to start now and just talk through some of the applications that we've used MT to study. And I'm going to talk about a couple of types of convergent plate boundaries, first of all, and then talk about subduction zones with a couple of examples. So obviously these plate boundaries are an important part of the plate tectonic cycle, and the difference is really controlled by buoyancy. In a continent-continent collision, we have two plates with low-density continental crust, and they can't be subducted. So we form large mountain belts such as the Himalaya and Tibetan Plateau. In an ocean-continent subduction zone, it's no problem to subduct the oceanic plate. So I'll show you some examples from Cascadia with MT and also from the Andes where we've been working in Bolivia. So in terms of continent-continent collisions, there are a couple of examples to look at. And obviously the best well-documented example is Tibet. India's moving north at 4 centimeters per year still, and has produced the largest area of thickened crust and high-altitude plateau on the surface of the Earth. Turkey is also sort of another collision zone. Arabia has been colliding with Eurasia, and while the plateau is not as high as Tibet, it provides another perspective on the time development of these collision zones. So I have a few slides at the end. If anyone's interested from Turkey, we worked there about 10 years ago. And I'm going to illustrate this section with work in Tibet. But what's really interesting, here is a GPS velocity map. This is now probably quite out of date, but this is the latest of the Chinese data from about 5 years ago, showing just what we can see from geodesy about the collision zone. India's moving north at 4 centimeters per year and is making this spectacular U-turn around the eastern Himalayan syntaxis. Now we can see across Tibet, these velocities are relative to Eurasia. We see a relatively smooth decrease in velocity across the collision zone. So in a case like this, someone says, well, where's the plate boundary? It's 1,000 kilometers wide. It's not a narrow boundary as in the oceans. So Chinese science has gone through a huge development in the last 10 years. They have a similar program to USA Sinoprobe, which has invested vast amounts of money in seismic MT and geodetic networks. So various models for collision zones such as this. Obviously a lot of people, sometimes you read their papers and they want to choose one model or the other. But what I'm really showing here is some different processes, and the question is not is it A, B, C, or D, but what percentage of each process is controlling the origin at a different time. So subduction must occur in the early stages of a collision to bring the plates together. And this example is for the Anatolian collision. Well, early models from the 80s of John Dewey and others had thickening as being one of the dominant processes, that you can thicken the crust simply by compression. And this model certainly explains a lot of things that we see in Tibet and old origins such as the Varoskites. Dan Mackenzie was one of the first to suggest that horizontal motion was significant. And we can see from the GPS, this is clearly happening today, that the mass balance of a continent-continent collision is controlled to a large degree by horizontal motion. There are those that would say that's all you need. Others would say you actually have to have some vertical process, some delamination. So that's shown down here. Delamination is often convenient for those that propose it, because sometimes detecting those pieces of lithosphere that's falling off is quite a challenge. So, end of the day, we're trying to balance the mass between the different processes. So, Tibetan collision was first studied by seismology, and here are a couple of increasingly old figures, one from Jim Nee from rather a long time ago, and a more recent one from Doug Nelson from the Indepth project. And it shows the use of modern geophysical techniques to study these type of processes. So Indepth showed that on a profile here in the southern Tibet, so the main boundary thrust is still where India is under thrusting. So this is a seismic reflection profile collected at quite significant expense, but showed very clearly, here is the top of the Indian plate that is subducting beneath Tibet, the main Himalayan thrust. Here you can see the moho of the Indian plate. So this shows us that the crust in this region is 80 kilometers thick because it's a sandwich of Asian above Indian crust. So George Airy, the geodesist, discovered this back in the 1800s. I suspect the price tag was rather a lot less than the $3 to $5 million that was required to do a large seismic survey. So seismic measurements in Tibet have made a huge progress in understanding the crustal thickness, and also understanding where there's regions of fluid. There's this large region up in the north here where S waves don't travel. It tells us that the crust and upper mantle is essentially liquid, or behaving as a liquid. So what can electromagnetics tell us about? So EM is often a very good complement for seismics. Seismics can see reflections from layers very well. What MT can do is it tells us the bulk resistivity. So if we combine the measurements together, we can often make a lot of progress. So I began working with Indepth in Tibet in '95 and spent a total of 8 months there over 4 field seasons. So here we are making MT measurements in Tibet. Here's the instrument. Here we're using low frequency instruments. We want to see deep, so they have to measure for about 3 to 4 weeks. So a lot of effort in this type of project, as with US Array, goes into basically making sure that you have permission and some mechanism for security and for instrument protection in place. Here we're burying the electric field lines. If you've got cheap labor, it's often a lot better to put them underground to stop them moving or being bitten by animals. So these are examples of making MT measurements in Tibet. And the results, number of profiles have been collected now in the Himalaya by white is Indepth, which was a US-Chinese collaboration. Dark blue are Indian transects. And a lot of them cross most of the main structures in the Himalaya. So here is an example. I'm just going to talk about what we call the 100 profile. And that crosses the main features at about 90 degrees east. So each triangle is an MT station, and what this figure shows is the results of inverting the data. So we're processing the data, finding a model which fits the data. We've really now in the last couple of years moved to fully 3D imaging, and we get similar results. But this illustrates the main points, how this method works. So we're seeing here in the crust, so here's the high Himalaya. This will be towards the south. This is the Indus-Sangpo Suture, which was the suture zone formed by the collision of India and Asia 40-some million years ago. And what's unusual here is, here's high resistivity with the Indian plate as expected, but Tibet is underlain by this very low resistivity layer that sits here. And trying to understand the properties of that require other constraints, because many things can cause a low resistivity. So one of the great things, this was one of the first CD projects funded by NSF that really sought to combine seismics and MT and other data types. So if we overlay the seismic reflection data that was collected by Indepth. Here you can see the top of the Indian plate. The main Himalayan thrust is here. And as expected, the Indian plate is highly resistive. It's Archean, Proterozoic, so it's dry, it's cold. Under Tibet, we can see a strong reflection from the top of this layer. So if, as had been proposed, this is a layer of fluids, we now have two pieces of evidence for that. We have a low velocity, and we have a low resistivity. So two pieces of evidence that this could be a fluid phase. So what fluids are possible down there? Could be saline water. We see that often in geothermal fields. Could be partial melt. So obviously with the depth and the very high geothermal gradient that's been measured in southern Tibet, this is probably corresponding to something around 600-700 centigrade. So wet rocks will begin to melt at those temperatures without too much of a problem. And if the rocks are dry, well, you may have to go a little bit higher. But we know this area has been under thrust. Water's been transported into the mantle. So this layer is believed by most who've worked in this area to be at least a certain amount of partial melt. Well, there used to be a way in MT, well, if the model was red or orange, it has to be magma, end of story. So what we tried to do was take this a little bit further and understand whether laboratory measurements can actually constrain the amount of fluid. So we're working here. This is a cartoon of a geodynamic model by Chris Beaumont that basically sought to try and explain the geology of the Himalaya with a geophysical model. And in their model, they noticed that in the high Himalaya, we have these granite-like rocks, leucogranites, which are being exhumed. And the ages of those are typically 15 to 20 million years. So in this model, we've molten a layer of the crust because of the thickening of the crust. The radiogenic heat can't escape fast enough, and you trigger melting. And with high erosion in the Himalaya, this layer is extruded to the surface. That's the idea of these models. So obviously for this crustal flow to work, the rock has to be sufficiently weak compared to the layers above and below. So what we tried to do was take the MT model and see whether our data were consistent with weakening that would allow flow to occur. So a figure on the left is showing the resistivity measurements. And this horizontal line here is 3 ohm meters. That's the observation coming from the MT. That was that big red layer. Well, you can show that to explain that with a silicic melt, probably something pretty felsic. Most of the electrical conductivity is the sodium ions in the melt. Water has a secondary effect. Everything else is basically irrelevant. So you're looking essentially at the sodium and the water content. And that requires probably somewhere between 5 and say 15% melt, depending on the composition of the melt. Well, then we kind of started looking at other compilations of what is the strength of these rocks. So this is a compilation by the group in Berlin, Claudio Rosenberg and colleagues, and they plotted strength of rock as a function of melt. And if you look in here, what you can see is in the past, people would use a log scale here, and that was often very deceptive. It's actually the biggest strength change occurs when the melt starts to connect on the grain boundaries. People used to call this, the significant thing was happening over here at about 20-30% melt, when the rock was becoming a liquid. But it's actually the early phases of melting when the melt connects on the grain boundaries that have the biggest effect. So what we can see is if we're looking at 5 to 15% melt in here, we're looking at an order of magnitude strength reduction compared to the dry rock. And if you read Chris Beaumont's papers carefully, that's what he requires. An order of magnitude weakening is enough to make the rock creep or flow over a geological time scale. So this doesn't prove that the flow is occurring, but it certainly gives support for the idea that that could be possible. Well, other parts of Tibet have had models of crustal flow proposed to explain the tectonics. And here's another large area. So a previous study, we were looking down in the Himalaya, where the crust has been thickened and erosion is bringing the rocks to the surface. A number of authors, the first ones being Maren Clark and Lee Royden, proposed that large parts of eastern Tibet could be explained in terms of topography by crustal flow. And in models like this picture just looks like a liquid flowing, doesn't it? We can see here. Here's the Sichuan Basin, which is a stable region with Archean crust and an upper mantle. And the idea is that the flow is moving around the stable regions into regions where it can lower the overall topography. So a very simple model. There are, again, as always with geodynamic models, people who believe them completely and others who are very skeptical. So there are other explanations for this area. But the idea is, if this is crustal flow, can we get geophysical evidence to support this? So a lot of Chinese colleagues have been working with MT since we began in Indepth in '95. I think now perhaps half of the MT instruments worldwide are commercially owned by Chinese companies and are used widely in academic and commercial research. So with working with Professor Bai Deng-hai from Chinese Academy of Sciences, we've worked on a large number of profiles crossing this eastern region of Tibet, looking for these flow channels. And what we were a little bit surprised to see was, here are these 4 transects around the eastern Himalayan syntaxis. So the idea is the crust is moving around here. We didn't see a low resistivity in the whole region. Rather, there were these 2 channels of low resistivity, A and B, that can be correlated from one profile to another. Some of the gaps are quite large, and they are in the process of being filled by Chinese MT experts. So this showed us perhaps that the flow pattern here, if it's occurring, was rather more complicated. And these could be channels of crustal flow, but I think what we now think is happening here is these are actually shear zones. There's good evidence that in this region of southeast China, in Yunnan, that the crust and upper mantle are all moving together. And what is happening is on the boundaries, you have these large shear zones. And shearing, if there's fluid present, will keep the fluid connected. Remember, the resistivity determines by the amount of fluid and by the permeability, the interconnection. So we kind of feel that this is showing us that there isn't maybe crustal flow in the way that Clark and Royden had proposed. Rather, the whole crust and mantle is moving, and we have these large bounding shear zones. Well, this area has also been the focus of intense study. 2008 was the Wenchuan earthquake, a magnitude 8 earthquake on the western side of the Sichuan Basin. And while this area was recognized as a seismic hazard, it really wasn't seen as being one of the more risky areas in China. So this is an example of the rupture of the Wenchuan earthquake at Bailu School. And you can see here there's about a 3 to 4 meter offset that was produced. Amazingly, these 2 school buildings survived the shaking, but unfortunately the teacher's residence at the end was completely destroyed. So this earthquake did not have obvious precursors. There was some paleoseismology there that had shown the past earthquakes, but it showed relatively low deformation rates. So one of the models that's been pushed by Clark Birchfield and others is the reason for there not being an extensive fold and thrust belt is that the uplift of eastern Tibet was by a sort of hydraulic crustal flow process. So in their model, we see a low resistivity layer here, a fluid-rich layer, that is basically forcing the eastern side of Tibet upwards. So this is one model that certainly fits the data, and we have subsequently had MT profiles right across this area that certainly support this model. Others would say there is sufficient folding and thrusting in the Sichuan Basin to accommodate this without having this hydraulic mechanism. But the hydraulic uplift as a contribution is certainly a good explanation. Well, switching for a little bit now to talk about subduction zones. And again, some of the questions that we're trying to answer with MT, we're trying to complement what the seismic measurements can do, and is we're trying to understand where the fluids have gone. So in a subduction zone, water is being transported in the plate, both as free water and hydrated minerals, and it's being released and to a large degree controlling the melting here in the mantle wedge. And through programs such as the Subduction Factory, I think we now have a fairly quantitative understanding of how much water goes into a trench and where it's being released into the crust and the mantle. So there's been a number of MT studies of subduction zones. I'll just show you a few samples. This is from the Canadian Cordillera, from the northern Cascadia subduction zone. So Edmonton sits here. We sit on basically Archean basement rocks. And between Edmonton and Vancouver, we cross the back arc into the subduction zone and finally to the forearc in the Pacific Ocean. So what does a MT section through here look like? This is the start of a larger project that we've been doing for the last 15 years. And this is a profile going from the ocean across into the continent. And what we can see is we know where the seismic data show the plate to be. What we can see is that, again, the downgoing Juan de Fuca plate is quite resistive. Above it are a series of conductors that are due to fluids being forced out. Here in the mantle wedge, we see a very intriguing conductor. This is the region where the 4-arc wedge has been serpentinized. There's almost no MOHO because there's no velocity change. And we see in this region a low resistivity feature. People used to believe that serpentinite had to be a conductor. I think the consensus now is, unless you have a lot of magnetite, that's not true. So probably the explanation for this low resistivity feature, this is down to, say, 30 ohm meters, this is because of fluids being released, which are actively causing the serpentinization. As we move further east, here is the shallow asthenosphere caused by fluids being released from the plate. And what we can see is there's often, for the asthenosphere, there's lots of explanations. Two possible explanations are that we have basically melting here, and 5% would be an upper limit to explain that resistivity. The asthenosphere would have to be up to 5% melt. Another explanation is possibly that it is because of hydrogen. Water has been dissociated into hydrogen and hydroxyl ions, and that could be causing the low resistivity. So, as everyone who works in this field knows, for a long time there's been two groups who've made these measurements of hydrogen content and their effect on resistivity, Karato and Yoshino. And for quite a long time they've had very different answers, incompatible by an order of magnitude. I think we're moving towards a resolution of that, but I think the details still have to be worked out. So explaining the resistivity at depth in, for example, the asthenosphere, where the fluids are coming off and causing melting, are still a little bit of work to be done. Well, this figure shows, interestingly, here's the volcanic arc. So this is the region where melting is being triggered down here. And a recent result from Rob Evans and his colleagues at Woods Hole actually looks in a lot more detail. So this is the CAFE experiment across Cascadia. And so they're a little bit south of the US-Canada border. And what we can see here is they've taken the MT seismic data analysis a little bit further and allowed a discontinuity to be present in the MT model. So as I said before, MT averages the properties. It doesn't see sharp interfaces, whereas seismic receiver functions, such as these, are very good at seeing sharp changes. So when you combine the two, it sharpens up the image. So here you can see the Juan de Fuca plate's highly resistive, and just above the plate is this region of very low resistivity, which is where the fluids are causing the melting of the mantle wedge. And you can trace that conductor, comes up to the surface a little bit west here of Mount Rainier. So this really shows, I think, a lot of potential for further integration of EM and seismic methods. It used to be people would work separately. Well, we'll just talk to finish, as time's going on, about some of the work we've been doing in the Andes. So here's a classic example of a well-studied subduction zone. And one of the interesting features that we see in the Andes is the fact that we don't have volcanoes everywhere. We have currently these three volcanic zones in the north, center, and the south, and in between we have a couple of flat slab regions. A lot of debate has gone on to what causes flat slab subduction. We were talking this morning about the laramide. It's clear this is something that happens quite often in subduction zones. But what actually triggers the transitions, what causes the slab to not be subducted steeply, but to go flat, is still really quite a lot of unknowns there. So I'm going to talk a little bit about work we've been doing in the central Andes, where we have another interesting feature, the Altiplano, which is an area of thickened crust up to 80 kilometers. Looks a little bit like Tibet in terrain, but it sits above a subduction zone. It's not in a continent-continent collision. So we've been working in the central Andes trying to understand some of the dynamics of that region. Well, there's certainly a volcanic arc. It's maybe not as productive. This is Volcansahama in Bolivia, and this is the highest peak in Bolivia, and it's an extinct or recently extinct volcano. So the German colleagues have started working in this area now for some 30 years and have a number of transects. Down here in the south, this was the Ancorp project of the Germans in the early 2000s, and they crossed from the coast in Chile into Bolivia. And they found that the Altiplano, this high plateau, was underlain by a very large zone of low resistivity. And one of the things with MT is it's good at seeing the top of a conductor. It's not so good at seeing what is at depth. So if I'd made this paper, I would have probably shaded this white or put some big question marks down there. MT sees the first conductor, and to get below that is a challenge. So that's a bit different to seismology, because in seismology you have the energy coming up from below. MT, it's top down, and that limits you in terms of how deep you can see. So this was explained. This feature here is located down in the southern part of the Altiplano, as has to be due to the large layer of partial melt, huge conductor, some ways similar to Tibet, even though the tectonic setting is a bit different. Well, Henry Brasser and colleagues collected another profile here in Bolivia and found really quite a different structure. What they found was, here's the Nazca plate going down, and the high conductivity, low resistivity, is really restricted to a vertical region in the mantle wedge. And interestingly, it is not below the volcanic arc. So volcanoes such as Sahama sit over here, so somehow the melt is migrating at an angle up from this melting region to the volcanic arc. So it's kind of quite unexpected. So again, I think there's a lot of evidence now that subduction zones, we used to think they were very much limited to along strike variations. This is an example like in Cascadia where the structure is varying along strike a lot. One model doesn't fit the whole segment. So in the Andes, what we've been doing, I've been involved in a project we'll talk about a little bit to finish with Cornell, where we've been looking in the southern part of Bolivia, where we have a region which has a very extensive episode of ignimbrite magmatism for the last 10 million years that Xander Silva's called the Altiplano Puna volcanic complex. So a number of very large pulses of caldera-forming eruptions. And underlying the region, here's the ignimbrites in the area of southern Bolivia. So you can see some houses for scale here. So these ignimbrites just cover areas of hundreds to thousands of square kilometers, and they extend hundreds of kilometers from the calderas. So this is really sort of ignimbrite magnetism on a huge scale. And a number of these have, produced, more than 1,000 cubic kilometers of ejecta. Well, this area is interesting because it's also underlain by a very large seismic anomaly. That was called by George Xantoner as the Altiplano Puna magma body. And its extent here shown in black. There's been some adjustment of the extent of it with various additional data, but there's a basic correspondence of the red, which is the calderas of the APVC, and this large magma body. So right in the middle of it is a rather intriguing volcano, Volcan Utrunku, which sits in the middle. And that has become the focus because it's undergoing a lot of quite broad-scale uplift. So using INSAR, this is from Matt Pritchard's paper, 1,200 volcanoes in the central Andes, only a few of them have shown these long-term persistent uplifts. And Utrunku is one of them. It's moving upwards at something like 10 millimeters per year. Hualcahualca in Peru had a period of uplift, but it basically shut off. La Azufre here, a bit further south, in Argentina and Chile, is not actually associated with a single volcanic structure, but you've got broad regions of uplift over 100-kilometer distance. So this region became the focus of a project that I'll talk about in a moment, looking at trying to understand what is controlling this. So here's Utrunku, and the inflation is focused and centered on this volcano, which last eruption was 200,000 years ago. It's surrounded by a zone of subsidence, which is very interesting. And once you get to the limit here, there is no deformation. So this is the Salar of Uyuni for reference up north. Here's the volcanic arc. So this volcano sits in the back arc, and it's been the largest region of uplift not associated with an active volcano that's been discovered to date. So the Plutons project is actually just winding down, was an NSF, a CD project. I think it gets I don't know who thought the acronym up, but it's pretty contrived. So our contribution with NSERC was to provide a third N to give some symmetry to the N's and the S's. I think this came out of University of Alaska Fairbanks, this name. I won't mention any names because it's being recorded here. But we have various South American colleagues, and the idea was to look at these zones of inflation and try and understand where is the magma moving. Clearly, because of the broad wavelengths of the uplift, it has to be a deep source, 20 to 30 kilometers. But are we looking at horizontal magma motion, or are we looking at perhaps melt being produced elsewhere? So remember, we're sitting in the back arc. So Plutons has been focused on a number of measurements. So here we are kind of looking in more detail at the volcano, and the INSAR very clearly shows that this uplift's 1 to 2 centimeters per year. It's been going on since INSAR began. Some of our colleagues, if you work in Bolivia, you spend a lot of time waiting for things to happen. They went to the government surveying offices and found indeed that the surveying in the 60s showed the same uplift. So Utrunku has been going up for as long as we've been able to measure. So in the Plutons project here, we've been doing, there's a passive seismic array just been pulled out. There's been MT, GPS, gravity, and a lot of petrology. So here we are, one of my students making MT measurements. So Utrunku is great for access. You can actually drive up here. The road's a little bit narrow, but you can basically almost, and then you can hike to the summit, 6,000 and some meters. So fieldwork in Bolivia is always kind of interesting. We spend a lot of time driving. This is the Salar of Uyuni, which is the best highway in Bolivia. You can do 100 on that, and I don't ever drive that fast on the other roads. And in the field, here we are deploying equipment. So the volcano is currently, the summit is here, and we're making measurements here with an MT station at the foot of the volcano. MT instruments are light enough to be carried if you've got the right resources, which here means Bolivians who are acclimatized. So with 4 or 5 people, you can backpack a station quite easily, several kilometers a day. And we made transects up a number of these valleys towards the summit. Driving in Bolivia, we also spend a lot of time getting vehicles that have been stuck somewhere, but it's all part of the game. So here's an example of the coverage we have, and this took 3 field seasons to do this, 2 in Bolivia and the last time in Argentina. So this is now a grid of our stations, and we've done 3D inversions of these, which we've just published in a geology paper, which is going to be in the March of Geology. So one of the first things we do is we can actually look and understand what is the strike direction from an array of instruments. And that's shown in this rose diagram here. And even though we've done 3D inversion, it's really interesting to look at those diagrams and those trends and see what they are showing. So here, just for reference, this is the uplift, and here is the subsidence area. So, you know, we planned this. The NSF proposal said we were going to do a nice uniform grid. Maybe Lindy was on the panel at that point. I'm not quite sure. But access is good here, but it's not that good. It's kind of, you know, you can do a 3D, but you can't really get everywhere. And with hindsight, perhaps some of these gaps could have been usefully filled, but it becomes a very long hike to do that. So, show you a couple of examples of data. Just MT, what we're doing is we're measuring resistivity as a function of signal period. So the seismic equivalent to this would be surface wave analysis, where the lower the period of the surface wave, the longer periods go deeper. And here we're measuring at one of our stations. You can see here, this is the resistivity that we're measuring as a function of period. So this corresponds to greater depth. And the red and the blue correspond to measurements in north-south and east-west. So what you're able to do from a single measurement, it's a bit like looking at SKS splitting, is one station can give you directionality. So we can see here that the blue and the red are the same, right the way down, and only at the lowest frequencies in the deepest structure is there some directionality, some 2D or 3D nature. So we can see here at the surface, it's high resistivity. There's a low resistivity layer. Then at the lowest frequencies, the resistivity drops off. So we can look at data like this and see that there are some layers present. And the lowest is very low resistivity. Well, here's an interesting station. This, I believe, holds the current altitude record for MT. And we were able to drive to 5,800 meters on the volcano and put a station here. So this is actually one of the easier ones we put in because it was in volcanic soil and ash. But again, thanks to the Bolivians, they do a lot of the hard digging at high altitude. These are near the summit of the volcano, and right next to a fumarole field, we can see very low resistivities, 0.1, 0.01. These are some of the lowest resistivities I've ever seen. And it's because we're sitting on top of the fumaroles that are still active in this volcano. Well, this is the summary. This is now our transect going all the way from the border with Chile into Argentina, right across this region. And here below, obviously this is dominated by this large red feature. So this is the APMB, the magma body detected by George Zandt and colleagues that underlies this region. And I'm going to Tucson this evening to talk to George and Sue some more about exactly, we're trying to reconcile the depths that we are getting from the MT with the depths that they get from the seismic tomography and from receiver functions. So we have about a 5-kilometer disagreement, which is not maybe so much, but it'd be good to resolve that. But what's interesting is to note is, here is this large magma body that's been feeding these ignimbrite eruptions. There's pathways that connect to the surface. So this is a 2D inversion. The 3D is actually very similar, but what we're including here is the topography. So near the surface, you can see there's a shallow conductive layer. That's probably clay alteration below the ignimbrites. Here's the APMB, the magma body, using constraints, for example, from Anne Pommier's lab measurements. This is probably 5 to 10% partial melt, basaltic melt. But these regions here are the various pathways that are perhaps being associated with magma making its way to the surface. Significantly, this melt layer domes up underneath Utrunku, right below the center of the uplift. So there are some in our Plutons group who think it's a coincidence that Utrunku is in the middle of the melt zone, but it's very striking. And here we have indeed a slight, about a 5-kilometer uplift below this feature. So this starts to show some of the complexity in a region where melt has been coming through the crust for 10, 15 million years. Obviously, if it's crystallized, you're going to get a batholith. But as it's intruding, you're going to get melts or fluids coming up to the surface. So this is going to be in the March edition of geology, where we have a 2D and a 3D inversion. So we're now at the stage of really not just stopping there, saying, well, okay, we've got this many % partial melt. Which geodynamic model is really going to be favored? And that's kind of a work in progress. This moat is significant, discovered in the INSAR, a slight subsidence. So there's still 3 types of model that could fit the data. We could have vertical motion of melt from somewhere down in a mash zone at the MOHO into the APMB, or it could be lateral motion, or it could be a diapir, has been proposed again. That was in fashion a number of years ago for granite emplacement, and others have argued that Utrunku shows evidence for a diapir in operation. So I'm going to skip forward. I was going to talk about strike-slip faults, but I think I'll just move to the conclusions. So hopefully, MT, I think, for certainly the last 20 years has been added now into these continental dynamic programs, and can actually say something. I think a lot of people have moved on from there used to be this competition between, MT and seismic, and it really wasn't very productive. But I think now that we're working together, trying to use each data set to sort of combine to get a synthesis, we can actually start to say a lot of things about the structure of the Earth and its properties and its rheology. So maybe crustal flow is going on in parts of Tibet. MT certainly shows that that's possible. It's weak enough to have flow. And in subduction zones, we're seeing the fluids going down for sure, and we're able to start to see, certainly in the Altiplano, the behavior, the magma dynamics of these melt layers. And I didn't talk about it at the end there, but we have a number of studies from large strike-slip faults. I first met Ramon Arrowsmith working on the San Andreas fault, and we now have a number of other studies of different strike-slip faults from around the world where we can actually start to put these in context. Most recently, we've done this in eastern Turkey on the Anatolian faults and on the Altentarg fault in northern Tibet. So, thank you for your attention, and I welcome this opportunity to visit ASU.